Good afternoon. Good afternoon, and welcome to the Concrete Institute of Australia. I'm John Nichols, Technical Manager for the Institute. It's my pleasure to be your host for this afternoon's webinar on Quay Quarter Tower, presented by CIA NEXGen. The CIA NEXGen series of webinars are organised and presented by the young professional members of the CIA to promote topics and generate interest from their viewpoint. They present a fresh approach to excellence in concrete. In this webinar, Tim Hansen will host, as Matt Obst will present on the project Quay Quarter Tower building constructed in Sydney. I'd now like to introduce Tim Hansen, who will formally introduce our speaker, Matt Obst. Ladies and gentlemen, please welcome Tim Hansen.
Thanks, John, and welcome everybody. As John mentioned, today's topic is the Quay Quarter Tower. It will be presented by Matt Obst from ADG Engineers. Matt has over 25 years international experience as a structural engineer and project manager, working for multidisciplinary consultants and as technical manager for major construction groups. He has fulfilled roles as ADG practice manager in London, Brisbane, and Melbourne. Matt has specialist experience in the design and construction of reinforced and post-tensioned concrete, in particular, the integration of post-tensioning into building structures to achieve economic and efficient construction. Welcome, Matt.
Thank you, Tim. Thank you, John, and good afternoon to everybody online. The building in front of us is quite spectacular at the end of the day. Has won a lot of awards for a number of different reasons. We're going to go back a few years in the talk today and look at how the solution developed and the challenges that were put in front of us at the time to achieve what we did with the structure, and in particular the reuse of a building that we can't see in this picture. But we'll continually try and remind you that there is actually a 50-story tower inside what you can visually see now. Quickly, this is me. We all spend probably a lot of effort trying to get 10 years experience on our CVs, and then before we know it, we're at 25, and I think I'm now at 30. So a little bit scary there, but it's every now and then in that period you get the opportunity to work on a project such as this. I'd also quickly like to acknowledge from AMP Murray Middleton. I've grabbed a couple of his slides here from a client's perspective, which I think is always good to have an understanding of, and Namal Pereira from Casina Consultants, who's also done a lot of work on this project with respect to review and also understanding the sustainability achievements of the project overall. Just trying to get a good control of my mouse here. So 50 Bridge Street. Remember that picture at the beginning? This is where it was 5 or 6 years, 7 years ago. Completed 1974. Pretty sure the drawings had on them 1971. Great to get hold of them. This is the tower that sat there. Very much gravity build construction. Not a lot of extreme activity in the lateral side of things compared to how we would build these structures now. Good heavy core walls, lightly reinforced because we don't let them have a lot of tension. I think the raft slab onto the sandstone was about 1.8 meters deep with a sheet of mesh in the top of it. So you can understand what we're starting with. But what we found as we went along, and we'll touch on, is a very well built structure. A couple of little surprises. But certainly in favourable condition for what we were looking at, as opposed to too many negatives. what we're looking to achieve. So we were tasked with looking at a building that, in its existing shape on the left-hand side, is quite rectangular. In order to achieve the third slide, which is extending and almost doubling the floor area of the building, we had to bring back the existing building slightly and then build out to achieve the shape and the architectural form. My next slide has a title on it. Why did we do it? And this is from a developer's standpoint. Location. I guess it's looking at a building and an asset that the AMP held. Looking to improve that, they faced challenges at the time around objections to whether it was going higher or building significantly more mass into a building. And the important area where they were able to achieve acceptance on development is, rather than looking at an individual building, they needed to present a future for the actual site or the block, having obviously AMP owning the tower at 50 Bridge Street, and historically the tower at the front, which is on the left-hand side of this picture here. So by presenting a solution in the future for the entire block and making sure that what they were then to propose would engage that area and combine activities in that whole zone, they were able to get approval for the project to go ahead. Why did we do it? Again, this is an AMP slide, so obviously there's an objective to increase lettable area. There's the location and the view. Why did they want to retain the existing structure? I think there was at the time, there's identified that there's got to be an opportunity there to do that. There is a building there that has a function. If they're not permitted to do an extremely dramatic change of style or go to a 100-story building or anything like that, given the location, a lot of that existing space was reusable, and that would certainly look then as a major benefit to the client. Cost estimates in excess of 700 million to go from the rectangular building to the new building. Again, there's that picture of the comparison between the two, and the reminder to everyone again is how do you fit that old building into that new building, and what complexities that brings on board. This diagram just is highlighting a little bit of the risk profile. It's important to understand. I mean, a lot of the time, depends where we are in the stage of a project. We get to look at what our own risks are. The risk profile here is very much about, and for this project was very much about understanding the risk to our client. It was understanding the risk to the end use, the risk to ourselves as consultants and designers, and also a risk at the end to the builder as well, and the construction methodology, and whether what was being proposed could actually be achieved. So there's a number of items here that really needed that buy-in, and part of the success of this project was that the client and the contractor and the consultants involved were prepared to buy into this risk profile, and in particular on the way the construction and the client relationship shared that risk at the end of the day, in order to make sure that what was proposed could actually be constructed. So there's a reliance on latent conditions, which is an understanding between all parties about what risks are there and what might appear down the track that you may not actually know now, or you may not have been able to define early on. As we go on a little bit further, we'll talk about how we then try and reduce these risks as well, and that's an important part of it. Non-compliance with deemed to satisfy solutions, understanding that the NCC allows us to do non-deemed to satisfy and look at performance solutions. Sometimes we should look back at what we do every day, and there's certainly lots of different code references now outside the Australian standards which need to be assessed on a performance solution basis. And there's no point proposing those unless you're prepared to verify them along the way. Safe construction methodologies, always important. Understanding what we can do is buildable. If we have challenges there, looking at redundancy, when we flick back and have another look at some of the photographs of the building, understanding the extent that the building structure cantilevers out towards the harbour obviously poses constructability issues. Understanding that in the structure, again, one of the items that is difficult to see on the current drawings is that actually columns in the basement and the ground floor was moved in level. So it was essentially removed as a restraint from the columns at the bottom of the building. Probably the last place you'd really want to do it. But certainly assessing on how we address that and how we're able to construct that at the same time. Condition assessments during construction, certainly material inspections, material testing, verification, and understanding that process, and accelerating construction sequence. I think construction sequence in general is where the risk is, and that's again understanding when you're demolishing and when you're building and when you're only partly demolishing a structure, is ensuring that you're able to model or replicate, whether theoretically or digitally, what the impact of that can be. And then it's also important to be able to monitor it and understand what the impacts of that are, so that what the expectations of movement is in particular, so that we know that where we're going is still on the right track. So the decision making at the time, demolish and rebuild, demolish the whole lot and rebuild. I can say over the last, since carrying out this project, at the time we first started looking at the project, I would have said 90% of people, if they were asked the question, would have said demolish the entire structure and rebuild it. I think that's where the industry was at the time. I think if you ask people now, and this is in great respect to this project in particular, but there's a couple others as well, I would say that 90% of consultants and contractors and clients would come back and say, no, we want to put more value on what's already there, and we want to partially demolish, retain some of the structure, and rebuild and achieve. And it's looking back, that's a really big achievement of this building and the industry in general, in recognizing that these possibilities. Forgetting there's a little slide pops up there. So saving 140 million. But as we'll look a little bit later on, there's some program advantages which probably became more valuable than the dollars on materials and construction. Retain the existing structure. And looking back on the project now and making some of the assessments with respect to sustainability and what was achieved on that. The conservation of embodied carbon, the industry getting more conscious now and more aware of being able to calculate what those values are, and putting a number to things is important. I know we struggled a long time as an industry to be able to create a datum to say what something relates to, or yes, it is better than what was done here, or it was better than what was done there, or it outperformed a standard. I think it's important now that we all move forward as the industry and be able to reference that at good design and design with maybe slightly different priorities is able to achieve better outcomes and better values of sustainability against the standards that are in the industry. As we reduce construction, we reduce the 2.7 years of base building operational carbon emissions. Again, able to get those advantages through the reuse of the structure, and reduction in lifetime base building emissions. The structural design concept. So The diagrams in front, I like to call diagram A, diagram B, diagram C. So it's what I like to refer to. A is what we started with as a structure. B, the removal, demolition of the front harbour side portion of the structure, and then C is the final end use building with the fully extended floor plate and cantilever structure at the front of the building. Conventionally, when we look at A, B, and C, and I think this is where the concept of the building design and the proposals that went forward made a difference in that. To get from A to B, to get from A to C, you've got to go through B, and it's what you attribute to B for me is where things get important. So we can knock down the entire structure and we can rebuild the whole thing again, which is saying that we give that picture B, we give that no capacity at all, right? So that's useless to us. Let's get rid of it. Well, we start to ask the question and say, what if we could give that some value? And there are a number of solutions put forward to the structure where there was a conservative approach to, right, well, maybe that building can do what it's doing now. And so we say that looks after itself. And then we'll add on another building to it. But then we have to fully stabilize that new building by itself as well. And what then that would then require is a number of lateral elements, and certainly with the shape, if you looked at the green portion of the permanent structure by itself, trying to stabilize that somewhat independently of what was already there starts to get complicated with bracing. It may obstruct some views of the harbour. It may lessen the architectural intent of the structure, a number of things like that. And really that's where our involvement started coming into the building, and the opportunity here was, okay, what do we need to do to get more out of that existing building? Are we prepared to give that a value in the structural design that is better than what it is now? How can we incorporate that and get something more out of it? And I think this is the change now going forward. It's about, okay, let's get in there, let's have a look at this and see what we can actually get from it. So B1 here, what is our residual performance of that building, and how do we then go and verify that? This is what I call B2, is the new structure. Can we incorporate that new structure and actually use it in combination with the existing structure and get a benefit out of it? Material strength. So the shaded ones here are the big ones I wanted to talk about. Material strength. Obviously, we can't determine residual performance without understanding what the strength of materials and structure is already. And then there's also B5, which is structural analysis. So then we look at what our software applications and what we're actually capable of verifying. And just jumping down the bottom, B7 there, active controls, there's a requirement to measure performance of what's there, and there's a requirement to be able to predict and over lifetime of structures make sure that things are following the expected route with regards to performance. So residual performance, let's have a quick look at what we had there, and this is a typical floor plate of the Bridge Street building. So we're looking at precast beams, precast planks in between. You can see how much that gravity core dominates this footprint. Precast columns on the outside were precast shells. What do I got? A quick summary there. Core raft, about 2 meters deep with a sheet of mesh, as I said. Good chunky columns where not massive columns, but a lot of them. Variations in concrete strength wasn't something I'd come across previously, but actually the use of what they called lightweight concrete in the core walls as they got further up the building. Although we were to find that some of the levels where where it was supposed to be normal weight ended up being lightweight, and lightweight ended up being normal weight. But these are things we deal with. There's not a massive difference between the two, thankfully. Wall construction, 600 at the base, 300 thick as we move up through the building. Significant variations in wall thickness as we come through. Reinforcement predominantly used on the project, 410 C-bar. Concrete strengths. I should have written the modern day equivalents next to those because I won't be able to work them out in my head. But sure, you get the idea. The stronger stuff goes at the bottom and the lighter stuff goes at the top. Sorry, construction of the existing building. Very happy to say that it well built. We surveying the floors, the floor levels at the core versus the outside of the building were almost identical. No major deformations identified anywhere throughout the floor plates. Very, as we said, couple of surprises in some walls here and there, but in general, a good correlation between what's on drawings and what was constructed and tested, and we'll get to testing in a little bit. What was the key to our solution in incorporating the old building with the new building? And that was what came to be known for us as the high performance buttress core, or the composite buttress core. So in removing the portion of the structure in red in the diagram on the right hand side, and then being able to then reconstruct a slightly expanded core. So with the core expansion is on the harbour side, the critical dynamic movement, etc., from left to right as we look at the drawing is then removed, and the critical performance then became the north-south as we look at the drawing, or up and down as we look at the drawing. So with the installation of all the cantilever structure on the harbour side of the building, it was very important for us to make sure that we dealt with the impact of that and the eccentricity of that load. That was the primary focus of expanding the core in that direction, and then being able to ensure that the performance in the perpendicular direction is still maintained at the same time. So what does adding that core give us? The core gives us some ability to manipulate the lateral performance of the structure. We can control the strength of that material. We had some variability or discussion to be able to identify the extent of that core. Some thickness materials. You'll obviously be going off in some people's heads like, okay, so how does a core that you construct now relate to a core that was constructed 50 years ago? So we're going to have a new core that's going to try and shrink. We're going to have an old core that's already done all its creep and all its actual shortening and everything under load. So how are we going to try and map those two so that the two actually perform together? We looked at alternative materials. We looked at, okay, can we get more control out of a steel frame? Or are we happy that we can work with concrete properties, concrete suppliers and reinforcement content, and actually be able to do something that a little bit smarter and get a little bit more predictability and control out of that core extension? Something that would come into play shortly is also construction methodology and their understanding of at what point that core gets built, or what point the building gets demolished and the new construction starts. And that ability to start to bring into play all those differentials of starting times and finishing times is where a lot more of the more intensive analysis started to come into play. And that's really where we'll start talking about movement control and movement monitoring. Jumping back quickly, of course, we took a snapshot early days of the building as it stood originally as well, to have that datum of performance out of the structure, and to also get a simulation of of developing a theoretical model of the building as it stood and being able to correlate that performance. So we knew there was a little bit more in that structure because our actual physical testing of that structure was giving a slightly better stiffness performance from what our theoreticals were. So we always knew we were working in a good zone with our solution. When we talk about material testing, again, I know a conventional structure, and quite often in the past when I've looked at making amendments to existing structures, we might test a column or we might test a slab in a couple of locations to see what the concrete strength is. What's on the page now is the code for one floor level. You can imagine that we would do this on every floor. We've got multiple testing locations. If I put up an elevation of the lift and stair core itself, understanding that we may have 10 different samples through a core wall as well, and why the obvious answer to why we do this, the more information we can get statistically, then the closer and better solutions and better material properties that we're able to use in our end solution. While I think when we started this project, the code, some Australian references, the AS references around reuse of existing buildings was quite limited. What was good to see was certainly the ACI had a good set of criteria for us. Euro had a similar set, and a lot of it is based on that statistical evaluation, making sure that again, the more information you can get, the more accurate you can be. And there's also that item that always sticks in my head from looking at these items, was that if you're able to actually test physically what's there and what strength has been achieved, you're statistically able to use a higher concrete strength than if you relied purely on delivery dockets or purely on a set of drawings that estimated what was there. In all cases, if you can physically achieve it and physically verify what's there, you're actually allowed to statistically use a better value. So the advantage in doing the work is well worthwhile. Of course, and unless you get a few surprises, and they're always there, but minimize them and know that they're there is what we're trying to do. Movement. I quite often say in these presentations on Key Quarter that what we've got in front of us there is the most simplistic version of a movement diagram on this job. There are a lot more there as we break down different stages of the project. The important thing to see here is the challenge that was put in front of us. So if the blue line is where we are at the very beginning, when we remove the harbour side portion of the building, what happens to the building? The building then wants to move away from the harbour, which is in this diagram is the orange line to the left. For me, it seems a little bit the wrong way around, but it will try and move away from the harbour because that's where its load is pulling the building. As we then build the new portion of the structure on the harbour side, it will gradually pull itself towards the harbour side, and eventually, when complete, because of the eccentricity in the cantilever of the structure, it will have a permanent deflection that is harbour positive. Now, if we underestimate the movement when we demolish the existing structure, as in we underestimate the stiffness of our existing structure, then it will not go far enough in the opposite direction, so that when we put the new structure on, it will go too far into the harbour. Hence the importance of getting these numbers right, and this is the most probably the most revisited portion of the project through all stages of design and all stages of construction. And the opposite of the opposite is action from an end result is good, but you risk then, if you get the building the existing core, because it is limited in its reinforcement content in the core, means it had a limited tensile capacity in the walls. So where in a more modern design we would put a relatively high rebar content, vertical reinforcement content in the walls to address tension issues, in the original building that reinforcement content was very light. So we had quite strict controls on what that capacity of that reinforcement was. We as part of the project, we did look at whether we had an opportunity to improve that and what methods were available to us. But at the end of the day, I think it was about limiting that capacity and being comfortable with where those movements, wall tension stresses were with what we had already available to us. We touched on construction methodologies as well. Harbour side here is on the left of the picture in the middle, existing tower on the right-hand side. Demolition has occurred from the top down of the front half of the core, while we accelerated the construction of the front of the new floor plate on the far left-hand side, and also accelerated demolition underneath what's essentially a hard deck there, is shown with a void underneath it. So what ended up being evaluated very early on was an opportunity to construct the new and old portions of the building on an accelerated program, which was immensely beneficial to the project overall and was delivered very successfully. These assessments were analysed early days. They needed to be to ensure that all those movements and the movement diagrams that we showed on the previous screen, movement, of course, is relative to stress, etc., in the cores, and understanding at all times that we're staying within the limitations of the materials that we had. On behalf of Namal here, and again acknowledging his screenshot here, just revisiting that risk profile again, and looking at, okay, what this design and what this project achieved, and it was that, again, is the risk profile and being able to have everybody buy into that and understand what their role was. Managing that risk, very much about enabling technology that was available to everybody involved, as much as material testing, understanding whether it's scanning or whether it's accelerometers, or understanding the performance of the existing structure as a whole as much as individual elements. There's a structure and its digital twin, obviously spoken about a lot these days around establishing that. That's from a design perspective, as well as from a documentation and detailing constructability perspective, as well. Obviously very important in this project to be constantly managing that process. That's the twinning process, and making sure that the two are aligned, reality and theoretical. The outcome and benefits, the benefits of being able to alter and deliver on a complicated build methodology, the outcome and benefits of ensuring that the areas that we're working in are within the capacity of what's available to us, and then acknowledging that the solution at the end of the day achieves what the architect and what the client and the end user intends to get out of it. What we achieve from a sustainability perspective, now a lot more common than what we were thinking at the time. The carbon footprint being, as I said earlier, being able to put a number against that, being able to acknowledge the massive benefit that was achieved through this project. And the one that we'll put out there is that cradle to cradle upcycling. And through this project, we talk a lot about being able to reuse a building that's had a design life for 50 years. But we kept putting forward again as like, okay, that's one cycle. So what's the next cycle? Are we saying that in 50 years, we're going to do this again? And what's going to change? And what, are we happy with what we've got there, that we can actually upcycle it again? And you start asking yourself the question about the job that's on your desk at the moment. And you say, hey, in 50 years, can I use this again? Can I do something different? Can this form the spine, or can this be reused to provide provide 80% of the lateral stability to another building? Is that the way we should be thinking as engineers? The outcomes of this project, again, is that structural performance and the ability to merge the old and the new. It's the end of the day, when we look at what we achieve from a carbon saving of 12,000 tons of CO2, we didn't go out of our way to do that. It was achieved by the project, by the general principles of what we were achieving with the structure. That was achieved through that process. To address buildings specifically with a target, we probably can improve on these things. And again, it's that sustainability consciousness in the back of the mind, saying, okay, well, should I actually be looking at how reusable this is in the future? And is that actually a way to measure structures and buildings, as we all look for try and get the benefits out of concrete longer term? Again, just a quick snapshot on the performance of the building versus a reference design of a new build structure, which may achieve 600 kgs of CO2 per meter squared, and the Mars analysis of the Quay Quarter project achieving 247. So again, a massive achievement by the project, and a great outcome for everybody involved. Is Quay Quarter Tower a model for the future? I think we've already gone through that cycle to some extent, as I mentioned earlier, where as an industry, I think our thoughts were at the time we started this project, and we're looking for solutions for the project, to where we are now is so much more focused on potential reuse of concrete structures. It's all going to come down to assessment of the building, assessment of what you've got to work with, and what you want to achieve out of it. But I think the industry, even for a couple of years now, is at that point where reuse is certainly one of the first options that are put forward on the table, and I think that's a great outcome that this project has helped get the industry to. So Quay Quarter Tower completed 2022. Again, I having been in the building and been sent so many photographs by people as well during the construction phase of the project on what was being achieved, looking at the building and understanding of what's in behind that shell and what's in behind the facade. And understanding that the solution that we put forward in very early days, what that's achieved and how that's performed, I think has been a great thing, and a really good addition to the skyline in the harbour, and the background to many people's photographs of Sydney Harbour. So that's where I come to an end. So thank you very much again for listening. There are many stories and presentations on this structure, and there's a number of different people involved that have had the opportunity to talk about it. And I think we all talk positively, and as I said, are very proud of the outcome. So thank you.
Oh, thanks very much, Matt. And thank you, John. That was fantastic. We've got a few questions coming through, so I encourage everyone online to please submit your questions. I'll kick one off with one of my own, Matt, that I jotted down during your talk. You mentioned the 50-year design life issue. How did you approach that when you've got sort of a substantial portion of your structure already approaching 50 years old to start with? How did you satisfy yourselves that you could sign that off for another 50 years to come?
I think that's the extent of the material testing that was carried out from a strength perspective was very much a statistical analysis, and those ACI references provide some very detailed methodologies to reference that. The other side of strength is durability, of course, and design life coming into durability, looking at chloride contents, covers. If I recall correctly, I think the chloride content was probably less than most of the modern concrete we get delivered, even after its 50-year design life experience. So that was great. There were some aspects of certainly the method of construction, which was common at the time, using precast shells and casting against precast shells, needed some fairly detailed investigation around some of those elements. So there were a number of aspects or areas that were specifically highlighted for further investigation, but certainly a really strong reliance on statistics for strength. And certainly when we look at strength testing, we're also doing chemical testing at the same time, and deeper investigation into the concrete to ensure that what was common throughout the project was good.
Yeah, thanks, Matt. There's been a couple of questions come through on the Q&A on exactly that topic, depth of carbonation and chloride testing. So it sounds like there was quite a thorough, destructive testing regime put in place before, I guess, the design went ahead. Is that right?
Yeah, for sure. Look, it was quality internally was all pretty good. There wasn't a lot of physically exposed concrete to the elements, other than the precast shells, as I said, which was an item which was identified early on as needing to be sure that those elements were all still hadn't suffered any durability issues over their design lives.
Yeah, great. Thank you. Another one from me. I imagine when you went into this project initially, there was probably a lot of unknowns at the start, and you could probably make your best guesses. And then as you went through your analysis and testing, you could define some of those unknowns better and better. How did you have confidence from day one that this was definitely going to be achievable and possible? And how did you give the client confidence, when they're investing $700 million that you could make it work?
Yeah, look, some initial testing on as I said, on the structure itself, and understanding what its performance was, and then being able to produce theoretical models that performed within those limitations of what was already there, was a big part about giving everybody that confidence, and trying to maintain performance of the theoretical modeling to say, okay, well, we know that the vibration in the structure is this. We know that we're able to understand the actual stiffness of the building. So provided the risk is you then accept that everything altogether works really well, but then you miss the one element that doesn't, is then where that testing has to back that up. And again, verification is a big requirement there. There is an allowance for dampening in the building as well, for a dampener, which is in the top, and so some of those aspects of being able to identify when those risks were raised to us, it's like, okay, so if we don't quite get that performance, or if we don't let you put that brace in because we want a better view of the harbour, what is the implications of that? And there's a lot of open conversation and a lot of verification.
Thank you. One question here. From the crowd, what was the primary structural design software used for this type of design, the theoretical modeling side of things?
Yeah, the theoretical modeling was an ETABS model. Part of the verification process along the way included a lot of review and joint assessment of modeling and assumptions that were made in the structure. So again, it's obviously an organization like AMP is not, as you mentioned, Tim, isn't going to jump in and let you spend all their money at too high a risk. So there's a lot of work there with other consultants as well along the way in ensuring that verification, maybe some slightly different views on things can be addressed and can be challenged. And so it's important that we're using a software like ETABS that there's a good understanding or a good peer understanding of in order to present that.
Did you have a complete thorough set of documentation of the existing structure, or did you have to supplement that with sort of scanning, GPR scanning, or exposing reinforcement and measuring it, for example?
On this one, while again there's verification and there's a lesser degree of scanning, we did have a full set of structural documentation, which was great to have. Some people spend a lot of time converting feet and inches into millimeters and meters and PSI into kilonewtons, etc. But it'll do them all good.
Very good. There's no more Q&As coming through on the chat, but if anyone else has anything else to ask Matt, now's your chance. Otherwise, we might wrap up.
Okay, thanks, Tim. And ladies and gentlemen, I ask you to join us in thanking our speaker, Matt Obst, and our host, Tim Hansen.